Welcome to The Explainer. Today, we're going on a pretty wild journey together. We're starting with this massive, honestly jarring engineering headache that we've all seen, skyrocketing AI coding costs. But we're going to trace that headache to a completely unexpected solution. We're talking about the creation of a mathematically bounded, licensable financial asset. Yeah, it's wild. Let's dive in and see exactly how a glaring technical flaw got turned into actual capital. Okay, let's dive into this. Here is our roadmap. First, we'll expose the token cost illusion. Second, we'll look at the paradigm shift of keeping AI in the OR. Then, we'll calculate the exact math of semantic bleed, map the grid, and finally, we'll wrap up with the AI risk Greeks. This agenda is going to take us from a harsh financial reality straight into actuarial risk assessment.
All right, Section 1, the token cost illusion, busting the prompt shrinking myth.
You know, the whole industry kind of just assumes that long, highly detailed prompts are what make AI agents so expensive to run. But the data, it tells a completely different story. Just take a look at this massive number, 1.6 billion. That is literally the number of cash read tokens generated from just one single real-world AI coding session. And get this, it took 3,486 turns to get there.
So the comparison here is pretty stark. The myth we're all fed is that you save money by aggressively shrinking your input prompts. But the absolute truth in the data shows us that preventing rework and dropping the turn count is what actually saves your budget. Seriously, a 550 token prompt injection just to keep the AI on track? That's a rounding error, especially when you compare it to the massive cost of an unguided AI endlessly rereading its own context over and over again. Let's actually break down those exact figures to see how this compounds. In that session, the input tokens were only about 575,000. The output tokens, 6.3 million. But that cash read, 22.5 million for creation and a staggering 1.6 billion for the reads. That is absolutely enough to make any CFO break into a cold sweat. Because here's the thing, when an unguided model hallucinates, it doesn't just read the context once. It rereads its entire history, including all of its own mistakes. And that cost compounds exponentially with every single back and forth turn. Moving on to Section 2, keeping AI in the OR, the paradigm shift. So if shrinking the prompt isn't the real answer, what is? Well, it requires a pretty massive paradigm shift, and I absolutely love this visual metaphor. Think of a surgeon in the operating room. You wouldn't want a highly specialized surgeon just aimlessly wandering the hospital halls, right? You want them locked in the OR, hyper-focused on the operation. Our operational goal with an AI agent is exactly the same. We have to prevent that context wandering. The aim is to drop those turns to success from, say, 8 grueling iterations all the way down to just 2. Because when it comes down to it, the only lever that moves real money is fewer turns to lean. We're not here to save pennies by cutting a few words from a prompt. We are talking about saving millions of billable tokens per task. It's all about optimizing the AI's behavior, not just restricting its input. All right, Section 3, calculating semantic bleed, the math of hallucination. Now, what's really interesting about this concept is how we objectively mathematically know when an AI wanders off task. I want you to picture a grid, like a physical 3D space of meaning. We essentially generate 2 distinct maps. First, we have the intent topography, which is a 3D heat map of exactly what you asked for. Then we have the reality topography, the heat map of the code the AI actually ended up building. We're directly comparing the shape of our original intent against the physical shape of reality. And as you might guess, when those 2 shapes don't perfectly align, we get what's called semantic bleed. It's the divergent mass. Think of it as the structural footprint of the executed code doing things you simply never asked it to do. It's reality spilling out into the dark spaces completely outside of your intent. And this absence, the space where reality exists but your intent does not, well, that is the exact mathematical definition of an AI hallucination. So how do we calculate this? The PMU Lens turns this into a concrete formula to find the exact ratio of divergence. Step 1, you measure the total weight of the delivered code. Step 2, you measure exactly what landed perfectly inside your original intent boundaries. And step 3, you calculate the bleed percentage, the absence. That gives you your final drift or sigma. So instead of guessing, we now have a concrete, totally defensible number for hallucination. This brings us to Section 4, mapping the grid, the dual engine. So where is all this math actually happening? It takes place on a 144-node semantic grid. We map AI meaning using what are called Chebyshev king moves. If you play chess, just think of a king moving one square at a time on a chessboard, tracking boundaries. This grid essentially dictates the physics of our semantic universe. If the AI's executed code crosses a categorical boundary and lands on a dark square on the grid, boom, that single step is logged as a critical semantic breach. And this brilliantly illustrates the dual engine architecture making it all work. It's a really elegant balance of breadth and depth. The gzip NCD component handles the breadth. It populates the grid by reading the repo, which is now about 15% dense, and places everything on permanent coordinates. Meanwhile, the Rust PMU handles the depth. It runs these fast, shallow, depth 2 walks to calculate the drift, but it does it without oversaturating the system. It's just a perfectly balanced ecosystem of meaning.
Finally, Section 5, the AI risk greeks, from code to capital.
Okay, this is where we escalate things from technical software architecture up to a high-level financial risk. We've talked about saving tokens for the CFO, sure, but the ultimate destination of the PMU Lens is creating a risk premium for the actuary, because a raw JSON debug dump, that isn't enough. Like the quote says, it has to be the licensable signal. We are talking about creating an auditable, trustless financial instrument that a reinsurer or an options writer would actually pay real money to license.
To pull that off, the system translates unpredictable hallucinations into actuarial confidence scores using the AI risk greeks. Let's walk through them really quickly. We've got delta, which tracks semantic delta, so actual placement drift and shape displacement. Then gamma, or traction gamma, tracking drift velocity, basically how fast is the AI wandering per iteration. Next is refolatility, which measures the variance of your injected rules hold rate. And finally, theta, tracking efficiency decay, which is your tokens per resolved commit. Put them all together, and you've got a comprehensive risk profile.
So bringing it all together, the PMU Lens takes raw text from your repository and transforms it into mathematically bounded instruments. It locks the data down using tamper-evident ED25519 signatures. It actually proves silicon provenance, meaning it guarantees this was a real hardware-executed walk, not just mock data. And ultimately, it calibrates these semantic breach rates into actionable price premiums. It takes a technical problem and turns it into a fully licensable financial asset. It's just brilliant. So as we wrap up, I want to leave you with a question about your own AI stack. Are you actually paying for AI outputs, or are you just footing the compounding bill for its rework? And in an ecosystem completely driven by unpredictable models, can you mathematically price the risk of your AI's semantic drift? Because we're looking at a completely new frontier for software and capital alike here. Thanks for joining me on this explainer. Keep questioning the data, and I'll catch you next time.